Imagine that your school gave a statistics quiz to 1,000 students with 5 questions, each worth 1 point. So the possible outcomes for scores would be 0, 1, 2, 3, 4, or 5. As you may already know, statistics, as a subject, includes a plethora of tools that will help us answer all kinds of questions and gain a variety of insights about the results of such a quiz. Did the students do well overall? What was the most common score? Were the results pretty homogeneous across a school or fairly mixed? Was it a sort of all or nothing quiz where students either seemed to get nearly all of the questions or none of them? You can learn a lot by answering these types of questions. Answers that would allow teachers and students to make decisions going forward about what to do or what to change or what to maintain about how they're teaching and how they're learning. And to be clear, we're using quiz results here as an example, but there's a million different contexts and different applications that this same sort of thinking can be applied to. Try to come up with one that might be relevant to your life, your job, or maybe a hobby that you're into, and see if you can think about it from a statistical perspective as we continue throughout this video. One of the first ways you might use some statistical tools to help understand these quiz results would be to make a frequency distribution chart. Now, we have a whole video on frequency distributions, but essentially this just means that we'll plot each score along the x-axis and the number of students with that score, in other words, the frequency, along the y-axis. That might look something like this. Data visualizations like this are a great way to get a quick understanding of the data. We can quickly identify, for example, that 3 was the most common score by far, and that very few students scored 0s or 1s. What are some other things that you can notice from this graph? There's a lot more that we can say here though, because this is not just a frequency distribution, but it's also what we call a discrete probability distribution. Now, that's a bit of a mouthful, and we'll get into what it means specifically in a second. But first, let's break down that first bit and recall that the word discrete refers to a type of variable. Think discrete versus continuous as the two types of random variables. Discrete, like this case, is when we have a finite number of listed values. Contrast that with continuous, which would be an infinite number of values, like a quantity that is represented by an interval on a number line. Discrete can mean quantities like number of students, where you can't really have half a student or like 4.8136 students or something. And continuous would be quantities more like temperature, where you can select all kinds of values in between any 2 degrees. There are also continuous probability distributions. In fact, there are a few other types, but for this video, we'll focus solely on the discrete variation. You might be wondering, actually, what this has to do with probability at all. After all, it's just the count of the number of students who earned each quiz score. Well, let's recall how we can define probability. The probability of a given event E is just the ratio of the frequency of event E divided by the total frequency. Or specifically for our quiz example, we might say that the probability of a student earning a 4 is the frequency of 4s divided by the total number of quizzes. So 297 divided by 1,000, or 29.7% in this case. In fact, we can compute the probability of earning any given score in this way. The probability of earning a 3 would be the frequency of 3s divided by 1,000, so 470 divided by 1,000, or 47%. What this actually allows us to do, which can be really helpful, is adjust our frequency distribution chart a bit. Right now, our y-axis is labeled with the number of test scores. This is fine, especially when we've constructed an example that has exactly 1,000 total quizzes. In practice, the number might not be as nice though, and the frequency of 297 3s might be a lot less insightful than just seeing 29.7%. So we can create a plot for a discrete probability distribution by just changing the y-axis from frequency to probability. Hopefully that starts to give a flavor for what we mean when we say a discrete probability distribution. We're using discrete variables and discussing how the probabilities are distributed across each result. There are 2 more specific criteria which we can highlight briefly. First, each probability must be between 0 and 1. We saw this when defining probability in a previous video, but hopefully that feels natural here since, for one, frequency can't ever be a negative quantity, right? You couldn't have -6 students earning a 4 out of 5 on a quiz. And 2, frequency of an event can't ever exceed the total frequency. You couldn't have more students earn a 3 than even took the test in the first place. So they must be at least 0 and at most 1. The second criteria is that the sum of all the probabilities have to add up to 1. In other words, if we added up the probability of earning a 0, a 1, a 2, a 4, and a 5, it's got to total to 1. This is because each probability represents a portion of the whole. And so if you take them all together, they have to add up to the whole. So here, we can compute the probability for each quiz score, add them up, and you can pause the video to check, but they add up to 1. So our example here meets both of those criteria, and thus represents a discrete probability distribution. Computing and visualizing probability distributions are great, but when it comes to quiz results, there is something else students are always asking about in order to better interpret their results, which we've neglected to bring up thus far. What is the average? More formally called the mean, you may remember that the average is calculated by adding up all of the scores and dividing by the total number of scores. But we have 1,000 students in our example, and adding up 1,000 scores could be quite tedious. And sure, there are calculators that can help us do this faster, but with our newfound understanding of frequency distributions, there's actually an even easier way. Since the probabilities of each score represent the proportion of data of each score and are all adding up to 1, we can find the mean by taking the sum of the product of the score times its probability. Now, I know that might feel like a lot to take in, but let's break it down. It's more straightforward than it sounds. We can compute the mean by taking each score, multiplying it by its probability, and adding them all up. So 0 times the probability of 0, plus 1 times the probability of 1, 2 times the probability of 2, and all the way up to 5 times the probability of 5. If we do that here, plugging in the probabilities for each that we calculated earlier, we get a sum of 3.212. So our average score on the quiz was 3.212. Awesome. Now it's worth noting that more generally, this can be represented by the formula here. Mu equal to the sum of x times the probability of x, where the sigma represents sum of and x represents your random variable. So for every option for your random variable, you multiply it by its probability and then add them all together. Like in our case, we used the numbers 0 through 5 for x, multiplied them by their probabilities, and found a sum of 3.212. So that's a pretty powerful feature of discrete probability distributions, but that's still not all. The mean is an often useful measure of central tendency, but doesn't typically paint the full picture of the data. Is it collected very tightly around the mean, or is it spread out really far? The variance and standard deviation are two other statistics that both can add to our understanding of a data set and can also be computed using information about the probability distribution. Variance, for example, can be calculated by the expression the sum of the quantity x minus mu squared times p of x, where mu, the fancy looking u, is the mean, and x, just like before, is the different values of our variable. So we could do 0 minus 3.212, 1 minus 3.212, 2 minus 3.212, and so on all the way up to 5 minus 3.212. Then square them, multiply each by their corresponding probability, and add them all up. This gives us a variance of roughly 0.70. Likewise, standard deviation can be computed with a similar formula. However, if we look more closely, we might recognize, or just remember, that standard deviation is the square root of the variance. So if we take the square root of the previous result, we get a standard deviation of roughly 0.84. And that is the power of probability distributions. We can visualize them a lot like frequency distributions to get some quick insights, as well as use them to help us compute different statistics like mean, variance, and standard deviation. If you have any questions, let me know. Otherwise, I hope you found this video helpful and have a great rest of your day.